Fluffy cakes, medical casts, and clean water are high-precision molecular tools. We manufacture them by balancing raw, opposing ingredients. To build tools at this scale, chemists first had to observe seemingly chaotic elements, carefully studying and cataloging them to harness their hidden power. The foundation of this design process relies on two distinct raw materials, acids and bases. They sit at entirely opposite, highly reactive ends of a chemical spectrum. Acids are sour and corrosive, while bases are bitter and slippery. The 0 to 14 pH scale allows chemists to measure ingredient volatility. These extremes operate inside us. Stomach acid maintains a highly reactive pH of 1 to 2 to break down food. This table details chemical indicators. Because we are dealing with invisible properties, chemists use these indicators as verification tools. They change color to confirm the exact nature of an acid or base before any mixing begins. Tracking these raw, reactive properties is the mandatory first step. We have to know exactly what kind of volatility we are dealing with before we can force these materials to build something stable. Chemistry is an active engineering discipline. Ingredients are deliberately forced into contact with other materials to see exactly how they break down and reform. This panel shows the first behavioral rule, the acid and metal reaction. When you combine an acid with a metal, like zinc and hydrochloric acid, the reaction releases hydrogen gas and leaves a salt behind. Moving to the next panel, we see a secondary rule. Crashing an acid into a carbonate produces salt and water, while actively off-gassing carbon dioxide. While the gases produced in these reactions can be useful, they quickly burn off or float away. The dense, stable material left in the beaker, the salt, is the true target of chemical design. The ultimate challenge in this manufacturing process is finding out what happens when the two extreme opposites, a raw acid and a raw base, collide directly. When they meet, the opposing properties mutually destroy each other's volatility. The corrosive burn of the acid and the caustic slip of the base cancel out, leaving behind chemical balance. This mechanism is called neutralization. The blueprint follows a consistent mathematical exchange. Acid plus base yields salt and water. The extremes cancel out. This specific reaction serves as the primary assembly method for the world's most stable compounds. Neutralization gives us a precise lever. It allows us to take chaotic chemical extremes and systematically engineer stable molecular solutions. Taking this process out of the laboratory and up to the industrial scale reveals where the base component of all these designs comes from. Sodium chloride is harvested in massive quantities from salt evaporation ponds. While salt is widely used as a seasoning, it functions in chemistry as a foundational engineering tool. It is the raw material we use to build more complex chemical solutions. By modifying that basic salt, chemists engineered baking soda. It's a compound designed specifically to react with dough, release carbon dioxide gas, and give baked goods their light structure. Washing soda is a salt engineered with water molecules to actively strip minerals from hard water. The adjacent graphic shows bleaching powder. It chemically traps chlorine power, releasing it on demand to purify water and clean fabrics. We even designed plaster of Paris, a specialized salt compound formulated to harden rapidly the moment water is added. It is a purpose-built material for setting fractured bones. Every one of these materials, from baking additives to medical casts, shares the same origin point in the controlled neutralization of acids and bases. The daily comfort and safety we rely on depends on raw materials forged deep underground, extracted and fed into complex industrial reactions. By forcing volatile acids and bases to neutralize each other, we extract stable, task-specific materials from the aftermath. Mastering these chemical properties allows us to design the physical world molecule by molecule.